So we're going to be looking at applications. And we'll start out with volumes, excuse me, and then we'll look at arc lengths, and then surface areas, and then work, and then moments of inertia. So the first, we're going to look at the first about two sections are going to be volumes. And then if we have time today, we'll look at arc length. But the idea with this, let's say we have some shape here. And if we take a cross section, if we intersect this shape with a plane, we're going to have a little area here that's our cross section. Now, what we're going to do, we're going to define a volume. So here's our little area. And we're going to project above this area a height. A little more similar. So we have a height. And now what this is going to give us is a volume. So we've gone from a cross-sectional area, and we have this sort of space here that's, if you can imagine this being filled in, that's going to be a volume. And so what this is going to look like, this height, we can call this height delta xk. So we have an area, and the height of this peculiar volume is going to be delta xk. So what's going on is this. Let's say we place this shape here, kind of have it hover over the x-axis. And if I'm going too fast, let me know. And so this volume, we're going to call it V sub k. And what it's going to be a slice of this shape. So this whole thing here is V sub k, this whole volume. And then you can see the height here. This is going to be xk minus 1, xk, and this is the delta xk. And this is A, this is B, where this thing starts and where it ends. So the idea is going to be this. Let's say of all these little cross-sectional areas with their little volumes attached, going from one end of this to the other. And so what we're going to do, we're going to add up all these little slices. And all these slices, as we go from one end to the other, that's going to give us the volume of this shape. Is it okay if I erase? All right. I'm going to assume that's okay to erase. So what we get is that the volume of this shape is going to be the sum of all the slices V sub k from one end to the other. And each of these slices well, it's a cross-sectional area at xk times that height, delta xk, or thickness. You could call it a thickness too. And so what we're going to do to get the volume, let me replace this equal sign with an approximation. It becomes equal if the limit as n goes to infinity, k equals 1 to n, axk delta xk, well, this will become the integral from the beginning of this volume to the end. And again, this volume's hanging over the x-axis, ax dx. Now here's the trick. We need to figure out basically two things: the bounds, and then we got to figure out the cross-sectional area of this shape as a function of x. That's going to be the trick to this. And you can, it's going to take it can take a little creativity. We'll do an example of how this can work. So this is what they recommend. And anytime they're recommending to draw something, that's usually good advice. So the sketch, the solid. And then with this sketch, we'll try to figure out ax. And then we'll find the integration. Limits. Then we integrate. A of x. So that's the challenge. Questions about that? All right, so let's take a look at an example. So let's find the volume of a 3-meter high pyramid with a base of 3 meters by 3 meters. Now, one thing we can do is we can place this thing on the x-axis so we can get a cross-sectional area that the x-axis passes through. So we can orient this so the x-axis passes through the area cross-section. So this is going to allow us to come up with A of x. We're going to want basically the x-axis to be perpendicular through the shape. So I'll try to do a drawing here of what this might look like. Any questions? Okay. So we're going to take this pyramid. We're going to kind of set it on its side. In a sense. I'll admit I'm not the best 3D pyramid artist. So I might have to bear with, again, some artistic license. So there's our pyramid. And what we're going to do, we're going to have the x-axis run right down the middle of this thing, popping out right in the center of the base, and then continuing on. So that's going to be x. And there's y. So it's going right into the tip of the pyramid, cutting right down the center, popping out the base. Now, a cross-sectional area, it's going to be something like this. It's going to be a square. It's going to be a square on the inside of this pyramid. Now let's take a look at some of the locations on the x-axis. This pyramid is 3 meters high. So that means where the x-axis pops through, that's x equals 3. So when it pops through at x equals 3, the pyramid is a base of 3 by 3. Now let's take a look at our cross section. So when the x-axis pops through the cross section at location x, well, that means this cross section is also going to be x by x. Ooh, that's not a, do this a little differently. So basically what's happening if we're popping out at x, the cross section is x by x. And so what this does is this gives us the dimensions of the cross-section area in terms of its location on the x-axis. And that's what AX is. That's what we want. So any questions about that? We're sort of just using this observation that since this pyramid is 3 meters high, the x-axis pops through the bottom of the pyramid at x equals 3, and the pyramid's also 3 by 3. So it has a base of 3 by 3. And this pyramid, being a pyramid, is going to repeat this pattern for any cross section down this pyramid. So when the cross section is sitting on the x-axis at location x, well, it's going to be an x by x area. So what this tells us is that A of x is x squared. So to find the volume of this pyramid, it's the integral from A to B, A of x dx, or the integral from 0 to 3 x squared dx, or x cubed over 3, 0 to 3, and this is equal to 9. So any questions about that? All right. So another method for finding volumes, and it depends on the kind of volume you're dealing with. But this is going to be called the disk method. And this usually involves a curve. It's a volume that comes from a curve revolved around an axis. So I'm going to go through an example to illustrate what's going on here. Excuse me. So let's say we have something like this. We're going to call this R of X. And let's say we're going to be interested in looking at things out to 4. Well, for a given X, the distance from the X-axis to the curve is, well, just R of X. Whatever X happens to be. So what we're going to do, let's revolve R of X around the X-axis. Pardon me. Ooh, need a second there to write that. So if we do that, we're going to get kind of an interesting shape. And the cool thing about these, we're going to start to get shapes that, well, we don't have like the, I guess you would say the canonical, we have these canonical formulas that have been handed down for finding certain volumes. This is going to let us find some non-canonical volumes. So here's our X-axis. Pokes out through here. There's our Y-axis. Again, to pardon some artistic license here. Let me do it on this side. So this is R of X, that height that we had. Here's the location X. Do a different pen. And so what we're going to get is this. We're going to create a disk when we rotate this thing around. And let's see here. With this disk, we're going to say it has a width dx. So what we're going to do, actually, we'll give it a width delta x. Call it delta xk. So we're going to do the exact same thing that we did with the volume with the cross section, because now the cross sectional area is a circle with area pi r of x, look like r of xk squared. So we're going to do this the exact same way as before. And so this is called the method of diffs, where we actually have a cross-sectional area. It's going to be the same formula every single time. We're not going to be coming up with the cross-sectional area new. It's always going to, well, it'll be depending on what R of X is, but the way we derive the formula is going to be the same way. Now that's if we're taking a curve and rotating it around an axis, then we get to do this. Again, if I'm going too fast, let me know. So we take our volume integral formula. This will now become the integral from A to B pi R of X squared dx. So let's go back to our example. Well, here, A is going to be 0, B is going to be 4, and the radius is R of X. So in this case, our integral is going to be 0 to 4 pi the radius square root of x squared. And just to kind of emphasize this as a radius, when you rotate this thing around, you're going to get something like this. So this is the other side of the radius. Here to here is a diameter. So only half of this is going to be the radius. So we'll get the integral 0 to 4 pi x dx. And that's going to come out to pi x squared over 2 evaluated from 0 to 4. And that's going to come out to 8 pi. Questions about that? All right. So that's if we rotate around the x-axis. Let's say we rotate around something else, a different axis. And we'll talk about the y-axis in a little bit, but let's say what about revolving around, let's say y equals 1. Let's do that instead. Well, again, we want to picture what's going on. So let's draw this in. So here's our, I'll call it f of x here, because it's not going to be the radius anymore. And let's say we have our y equals 1. So we're going to revolve this around y is 1. And again, we're going to stop at 4. Well, it turns out that the intersection point is 1, 1. And so what we're going to have is we're going to take this shape that has this axis of y equals 1 underneath it. We're going to rotate this shape around y equals 1. So now let's take a look at our radius. What does it do for our radius? Well, now that radius, r of x, is going to be the difference between the top function and the bottom function. That's going to give us that distance. So it's square root x minus 1. So we're going to take this little piece, rotate it around this axis. We're just going to get a smaller kind of vase shape. It's going to be that same vase shape, just going to be smaller. And then now the boundaries, instead of being 0 to 4, it's going to be 1 to 4. So when we rotate this, this is what it's going to look like. Here's that axis, y equals 1. Oh, sorry, we're not going to go quite that far. I apologize. We're going to go to here. That's the shape that we're going to get when we rotate this. So let's do the calculation. Again, any questions about this? So v equals 1 to 4 pi, and it's still going to be r of x squared except this time r of x is square root of x minus 1 squared dx. And so that's going to give us integral 1 to 4 of pi x minus 2 root x plus 1 dx. And that's going to be pi times x squared over 2 minus 4 x to the 3/2 over 3 plus x from 1 to 4. And if we hammer out the arithmetic on that, what we're going to get in the end is 7 pi over 6. questions about that? Now, you can also revolve these shapes around the y-axis. We can also do that. And so in this case, we're going to be integrating along the y-axis. So integrate from c to d, a of y dy, or the integral from c to d, pi r of y squared dy. So same idea, it's just we're going to be using integrating with respect to y instead of x. So let's say we're going to do this. We'll find the volume of a solid generated by revolving the region between y equals 2 over x and the y-axis around the y-axis. And we're going to put some limits on y here. We'll put y between 1 and 4. Now, what's going to help with this? We're going to put things in terms of y. So first off, y equals 2 over x. We're going to solve that so we get x is 2 over y. We'll solve for y. And again, let's draw a picture. Let's take a look at what's going on here. So again, this is our x-axis, this is our y-axis. I'm keeping this orientation, but if you want to flip things around, you can. The difference here, so let's say we have y is 4, and y is 1. So now we're going to try to look for a radius. Now in this case, though, the radius is going to be here because we're going to be rotating this around the y-axis. So our radius is going to be this way. And in this case, the radius r of y going to be 2 over y minus 0, or 2 over y. The distance from here to here. In fact, let me emphasize that that was what we're looking for right there. So questions about that? So this means our integral from c to d, pi r of y squared dy is the integral from 1 to 4 pi 2 over y squared dy, or the integral of 1 over 4 pi over y squared dy. And if you hammer out this integral, what you're going to get is 3 pi. Questions about that? So there's one more scenario to consider. And again, if we revolve around something that's, again, a vertical axis like the y-axis, but not the y-axis, say something else like x equals 3. And again, if you need me to wait, I can wait. So let's take a look at something like this. So find the volume of a solid generated, I'm going to abbreviate generated, by revolving the region between x equals y squared plus 1 and x equals 3 and x-axis. Oh wait, no, we're not going to do that. Yeah, no, we're not going to do that. Just x equals 3 around x equals 3. So we're going to graph this thing, get a sense of what's going on. So this is what x equals y squared plus 1 looks like. And we're going to have 3 here, x equals 3. And where these intersect, negative square root 2, square root 2. I'm going to revolve it around x equals 3. So we're going to get a cross-sectional area that looks like this. Well, yeah, that's what we're going to get for a cross-sectional area. This would be around x equals 5. So to do this, we're going to come up with a radius. So if this is the diameter, We just want the radius r of y, or the distance from x equals 3 to x equals y squared plus 1. So r of y is going to be 3 minus y squared plus 1. And this will simplify to, sorry, I'm running out of space, 2 minus y squared. All right. Put the 3 over there. All right, any questions? So now we'll do the integration. We're starting at 1, we're going to 3. Oh no, we're not starting at 1, we're going to 3. We're integrating along the y-axis, not the x-axis. So r of y squared dy, the integral from negative radical 2 to radical 2. And it was 2 minus y squared squared dy. And you can FOIL that. And if you hammer out the integral on that, you're going to get this. Over 15. So questions about that? So that's it for section 6.1. That's this idea of using cross-sectional areas, or more specifically, you can actually come up with a particular kind of volume when you have a curve revolved around a vertical or horizontal line. And that volume, you can use the method of DIS, where you use a circle as your cross-sectional area. But now in 6.2, we're going to consider a different method. And this is what's called cylindrical shells. Now, the idea here is this. We're going to approximate the volume using nested cylinders. So the idea is going to be this, and this might seem kind of strange. Let's say we have some cylinders. We got them sort of sitting in here, sort of like what they used to call the Russian nesting dolls. And the idea is that this would approximately represent, here, I'll put one more in here. Something kind of like this. There you go, three-dimensional object here. It looks like a gumdrop. So this is approximately that. So what we're going to do, we're going to add up all these cylinders. Now these are hollow cylinders, and they're going to have a little bit of a thickness to the walls, is what they're going to be. So hollow cylinders with a kind of wall thickness. So they're going to have a wall thickness. So it's going to be something like this. So this would be a cross section of one of these cylinders. And the height of these cylinders, it's usually going to be f of x. And there's going to be a width, delta x. And then the cylinder is going to be centered on some sort of axis. Usually it's like x equals L. We'll just call it L. X equals L, y equals L. And it's going to have a radius. And typically what this radius could be, it's usually x minus L, or L minus x, or it could be y minus L, or L minus y. Those are typically the formulas for the radius. And I'll show you why that turns out that way. So the volume of this thing, if we take this and look at it from another point of view, let's actually look at it in 3 dimensions. Take one of these cylinders. It's going to look something like this. And a little bit of dress work in here. There we go. So that's going to be our cylinder. So the height of this thing will be, say, f of x. The width is delta x. Right here. It'll be delta x for the width. And then here is the radius. So what we can do with the cylinder is we can slice it down the side and unravel it. And so this is the dimensions that we're going to get. So there's that thickness delta x. So if we unravel, so we have the height delta x, I'm sorry, f of x. Here's that thickness delta x, and then the length of this volume, well, this is 2 pi times the radius. So if we take the cylinder and unravel it, now we can compute its volume. Delta VK will be 2 pi times the radius times f of xk delta xk. So each one of these cylinders has this volume. And if we think back to that picture of the nested cylinders, if we compute all the volumes of those nested cylinders and add them up, well, we get an approximation to the volume of that gumdrop shape. So any questions about that? All right. So what we'll get is the volume is approximately k equals 1 to n of all these little cylinder volumes. And that's going to be the sum k equals 1 to n 2 pi times the radius times f of xk delta xk. I'm going to make a little note here with f of xk. Sometimes the height could be a difference of functions. So we might be more generic and just call that the height. So then the volume will be equal to the limit as n goes to infinity of this sum of 2 pi times radius. I'm just going to go with times height times delta xk. Or this is going to be the integral from a to b 2 pi times radius times height dx. Questions about that? All right. So let's take a look at an example. Now, they give some advice on how to do these, just like the other problem. So first off, we'll draw the region. Now, again, this is for objects that are being revolved. And it's just a different way of calculating these other than the disk method. So we're going to draw the region that's being revolved. And then we'll draw a line parallel to axis of rotation. And we'll go through why you do that. And then we find the limits. And then we integrate. The limits of integration, not to confuse it with other limits. So we found other limits, different type of limit before. So let's do an example. Now, what this does, it's in a way an alternative. Like, we're going to deal with something that's rotated around the y-axis, and in this example, and before we would integrate along the y-axis using disks. Another term for that is the washer method. They also call it the washer method. But let's say we're going to rotate region bounded by y equals x squared, y equals 2 minus x, the x-axis, around the y-axis. So when we do this, let's take a look at what we're doing. Let's draw a picture. So we're interested in this region here. So we're going to take this region and rotate it around the y-axis. This would be a cross-section of the whole thing. And usually what we would do in section 6.1 is we would create a radius here, and then we would use that, our pi r squared, we'd integrate from here to here. Now the problem is the radius is going to change its formula when you get to y equals 1. First radius will be this line minus the y-axis. But then the second radius is going to be this curve minus the y-axis. So you're going to have to do two integrals using the washer method or using the disk method. But with the cylinder method, we can keep it to 1. And so what we're going to do is draw that line parallel to the axis of rotation. The axis of rotation is the y-axis. So we're going to draw a line that's parallel. This here is going to tell us the height of our cylinder. And so the height, in this case, it's not going to be f of x. It'll be 2x, 2 minus x, minus x squared. That's going to be the height. Now let's take a look at x. So given a location x on the x-axis, this is the height of the cylinder. The cylinder is going to be something kind of like this. So this is the height here to here. That's the radius. So the radius is going to be x minus the location of the rotation axis, which is just 0. So it's just going to be x. So that's going to be our radius. So any questions about that? This is our cylinder. So now we can do our computation. We know the height and we know the radius. And what we're going to be doing for our bounds, we're going to go from x is 1, or really from x is 0 to x is 1 along all the possible radii for this cylinder, or for all the cylinders. So be a to b 2 pi radius height dx. Oh, a to b. With an integral from 0 to 1, 2 pi times x times 2 minus x squared. And just for the sake of time, I'm just going to give you the result from doing the integral here. You'll get 5 pi over 6. Questions about that? So let's take a look at another situation where we're going to actually rotate around the x-axis. Again, if you need me to slow down, I'm on erasing, just let me know. So let's say we have this, a region bounded by these curves. We'll rotate around y equals 2, and we'll keep y greater than or equal to 0. So what is this going to do? Let's take a look. do a little bit of changes. We're going to center this a little more. Points of intersection there. And then we're going to have y equals 2. Let's see, in this one, x equals minus y. So that's the graph of our functions. Now the region that's actually captured by this is going to be this. That's the region that's inside all these curves. And that's what we're going to get. So questions about that? Now we're rotating this around y is 2. So we're still going to have this. As our axis of rotation. So what we're going to do, let's draw that parallel line, the line that's parallel. The parallel line gives us the height of our cylinder. So our cylinder is doing something kind of like this. This is a cross section of our cylinder. And so the height, well, it's the difference between this curve and this curve. So that's going to turn out to be y squared minus negative y, or y squared plus y. If that's too small to see, please let me know. Now the radius for this one, well, here's our radius. Now for a given y, you can see that there, but that's a y. If I could put a little hash mark there and write a y, that's what I would prefer to do. The radius is the distance from this y position to the axis of rotation. Let me see. Oh, no, I'm sorry. Oh, yeah. Yeah, we're going around that way. So in this case, that distance, the radius, is going to be 2 minus y. So if we're located on a position on the y-axis here, the distance is going to be 2 minus y. I apologize. I think I'm slipping into a different kind of problem. I apologize. Let me let me just set this one up again. I apologize. I think I'm segueing into a different problem I didn't want to show you just yet. We're going to rotate this about. Yeah, I see. We're not going to rotate it about y equals 2. I apologize. That's the thing. I want to save that for later. And we're going to rotate, I apologize, around y equals 0, or the x-axis. I was looking at this, I was like, wait a minute, something doesn't look right here. We're going to talk about alternative horizontal axes. We will get to that. I want to go do this just around the canonical axes. So again, what we're going to get. And so the region that's bounded by these three things is going to be this. And we're going to rotate it around the x-axis. I apologize. We're not going to rotate around y equals 2. We're going to go around the x-axis. We'll do a version of this in just a little bit. But let's do the standard version of it first. Yeah, we'll do the alternative one, but let's do the standard version of this kind of integration first, just so we're familiar with it. And so what we end up getting is something like this. So the top of it here is y is 2. Down here it's 0. And then what we're going to do for a given position y, we pick a point on the y-axis. The height what's going to be this curve minus this curve. And that's still going to turn out to be y squared minus negative y, or y squared plus y. Now the radius is going to be the distance from this y to here. So we have a height and we have a radius. And the radius and this the distance from the y location to the x-axis. And that's just going to be y minus 0 or y. So we have our height and we have our radius. And those are the two things we need to find to use this formula. So we're going to be integrating with respect to y. So we'll go c to d, 2 pi radius, height, dy in this case, or the integral. So all the possible radii, you're going to have from 0 to, you're going to have from 0 to 2, and then everything in between. Two pi y, and let's see here, y squared plus y dy. And if you hammer out the integral, 40 pi over 3. Okay, so now we'll do sort of the non-standard one. We'll do rotation around an axis that's not the X or Y axis. We'll do that now. So let's say we have a region bounded by y equals x cubed, y equals 8, y equals 0. And what we're going to do, we're going to rotate this around not the X or Y axis, but around X equals 3. And it's bounded by another thing in here. It's also bounded by X equals 0. So if we graph this, it's going to be kind of a first quadrant sort of thing. We're going to get something like this. There's our y equals x cubed. Here's our y equals 8. I'll emphasize the x and y axis. And then there's x is 0. So this is y is 8. Y equals x cubed. And where these intersect, 2, 8. So if we pull this little region out, we're going to get something like this. So that's the region bounded by y equals x cubed, y equals 8, x equals 0, y equals 0. And y equals 0 we really technically don't need. But we're going to rotate this around, not the x-axis, not the y-axis, but we're going to rotate it around x equals 3. So let's see what this looks like. So any questions about that? So there's x equals 3. Now, we're going to come up with cylinders. So we need a height and a radius. So we pick some location x. Now again, these intersect at 2 and 8. So a given cylinder, it's going to look something like this when we rotate it around. So we need to come up with a height, and we need to come up with the radius. Now the height, what's this going to be? This distance here. So this curve, which is 8, minus this bottom curve, which is x cubed. That's going to give us the height of our cylinder. Now, what about the radius? Well, it's the distance from here to here. So that distance, our radius, will be 3 minus x. So that's going to be our radius, and that's going to be our height. So any questions about that? So now we do our integral. And again, we're going to integrate from 0 to 2. But 2 pi. Now, as we integrate along the region is what we're going to do. We're integrating along the region. Radius is 3 minus x. And again, that gives you all possible radii, because your radii can go from here to here, or from here to here. And then we have all the radii, in a sense, terminating in between. So from here to here is the shortest, here to here is the longest, here to here is sort of in the middle. So we need to go from 0 to 2. That's going to capture all the radii that we can get. So we have 0 to 2, 3 minus x. The height is 8 minus x cubed, and then we have our thickness dx. And then if you hammer this out, it's quite an integral, but what you'll get, 264 pi over 5. Questions about that? So now let's take the same region, and instead of rotating it along a vertical line, let's rotate it along a horizontal line. Or rotate it around a horizontal line, I should say. So let's take it about y equals -2. So what is this going to look like? Oh, let's say -1. Let's go -1. We have our region here. But now we're going to do this. We're going to have this other axis of rotation down here. So what we're going to do, we're going to be integrating along the y-axis. So let's pick a location y. Well, we need the height of our cylinder. Our cylinder is going to do this. It's going to do this. And that's going to be our cylinder. So again, we need a height and a radius. So the height of the cylinder, it's going to be the distance from this curve to the y-axis. Now, in this case, we need to be careful. We had y equals x cubed for this part. That was that curve. So we need to put this, since we're integrating with respect to y, this becomes x equals y to the 1/3. So the height will be y to the 1/3 minus 0, or y to the 1/3. So that's the height. Now the radius is the distance from y to this axis of rotation. It's going to be radius will be y minus -1, or y plus 1. So we have our radius for our cylinder, we have our height for our cylinder. We're good to go. So the integral from c to d, 2 pi radius times height dy will be the integral. And we're going to go from, we think about this one, you want to be a little careful. We're not going to look at our units or our limits. These intersected at 2, 8. So this is 8, and down here is 0. So we're going to integrate along the region here. They're all possible radii. The longest radii would be from here to here. The shortest radii will be from here to here. So got to integrate everything in between. So this will be 0 to 8, 2 pi, y plus 1, y to the 1/3 dy. And if we hammer this one out, 936 pi over 7. And that is going to be our answer. Questions about that? Well, that's it for today. I'll take a look at the homework schedule, make sure that's still making sense. What's going to happen for the rest of the semester, we'll do the test on Wednesday, and then we'll do probably 6-3, 6-4, and 6-5 the following Monday. They're short sections. And then that last Wednesday, we'll do 6-6, the part on moments of inertia. And then that's going to be it. And then the next time we meet will be Monday, and that'll be the final. So if you have any questions or concerns, please let me know. Other than that, have a wonderful afternoon. And if you have any questions on the homeworks or anything, please let me know.
Professor Coburn, in regards to the